In this last section from chapter 15, we are talking about angular momentum and conservation of angular momentum. And we see that show up in, for example, uh, the travels of satellites around the Earth. They travel with elliptical orbits, and because the forces acting on them are what they are, that it means the angular momentum is conserved, and so they don't require quite as much energy. But we do need to get that initial linear momentum accurate so that it gets caught appropriately by the gravitational forces, and we can take advantage of the conservation of angular momentum. Or you may see rides like this, where passengers are sitting in their seats and the machine is spinning around. The faster it goes, the further they leave from the central axis. The slower it is, the more they get pulled in. And if we look at these forces down here at the bottom, we can see that the weight of the passenger is parallel to the z-axis. And the normal on the seat of the ride back towards the passenger goes up through the z-axis. So neither one has a moment arm that would cause a moment about z. And that's kind of an interesting little feature. And so summing these moments about the z-axis would be zero. And yet the whole ride is spinning about the z-axis. So it's a little different there. So when looking at angular momentum, just as a reminder, linear momentum is force times the perpendicular distance from the point about which we're taking the moment to the line of action of that force. We often called it D. So moment was force times distance. And that was very particular, the perpendicular distance. If we struggled finding that perpendicular distance, and we did this in statics, then we would find a position vector from the point about which we're taking moments to anywhere along the line of action of that force. And we called that position vector R. And then when we took the cross product of that position vector with the force vector, we were given the moment vector, which was perpendicular to the plane in which the force was moving and went through that point. Well, now with angular momentum, it doesn't work quite that way. What we're looking at is the moment created by the particle's linear momentum. So we're taking that linear momentum, which is mass times velocity, and we are multiplying that by the perpendicular distance to the point we're looking at. Or again, if it's tough to find that perpendicular distance, we'll take R, a position vector from the point we're taking moments about to the line of action of that linear momentum. So it's an R cross MV, and we call that H naught. The magnitude of H naught would just be mass times velocity times that distance. So it's very similar to the moments we took in statics, only now it's angular momentum because we're taking a moment and treating that as if it were causing a rotation about the point. And the force resulting from that is equal to the time rate of change of the momentum. So that's the v dot that we're talking about. Now, I don't often see that showing up in the problems we're working. This is just kind of background information. But through math and a little manipulations, we can prove that the moment is indeed R cross F or H naught dot. This also works not just for particles like we've been talking about, but entire systems as well. And so we could find the R cross F for all of these individual particles, and that would give us that angular momentum, the time derivative of the angular momentum. So that works out as well with a system, just as it did with an individual particle. And notice once we integrate that particular equation from T1 to T2, we end up with what we call the principle of angular impulse and momentum. And I tend to use this version on the right side more often. It's very similar to our work energy equation, where we had T1 plus the sum of all of the work acting on the object equaled T2. Well, this time we're taking our initial angular momentum, adding the sum of all of the moments caused by this, well, all the moments acting on the object, and that will give us our final angular momentum. Now, the sum of all those moments we call the angular impulse. And you can think of maybe the game tetherball, where you get the ball going and it goes with a particular velocity, and then you give it another hit as it goes by you, and that's providing a new moment, a new force acting on there. It's an impulse that increases the speed of that ball, and hopefully you end up winning the game. If all of those impulses, however, sum to zero, we get the conservation of angular momentum, such that the initial equals the final. And you would see that when, for example, the forces on the particle were all acting towards that point about which we're finding a moment. Because there's no moment arm on that force, it creates no extra moment. So no extra impulse acting on the particle. Much like those forces we looked at in that carnival ride, those created no moment, so there would be no impulse there. So let's look at it, this sample problem. This will give us a better sense for what we're doing. We've got two identical 10-kilogram spheres attached at the end of this rod, and you can see they're equidistant from the center, 0.5 meters. They're subjected to a 10 Newton force, both top and bottom, well, both acting in the same direction from an angular perspective, both causing counterclockwise rotation. Plus, there's an added moment added on the rod of 8t Newton meters, where t is in seconds. Now, they want us to find the speed of the spheres at t equals 4 seconds if the system starts from rest. They suggest we apply the principles of conservation of energy and conservation of angular momentum to the system. So we'll have perhaps some energy and some angular momentum. So here's the problem. Let's see if we can work our way through this. Now we've got our equation. We had H naught plus the sum of all of those moments acting on the system will equal our final angular momentum. So note that the system starts from rest. Since it starts from rest and our angular momentum is mass times velocity times distance, we've got mv times d, and we know that v is 0 when it starts from rest, so mass times velocity, mass times 0 times d will be 0. So our initial angular momentum is 0. And what we really need to pay attention to now are the momenta caused by the 10 Newton forces, as well as the moment on the system over time from T1 to T2. Now we're starting at rest at T equals 0, and we're going to T equals 4. So we're going to take the integral of 10 newtons times its distance, which is 0.5 to the center, and we have two of those actually. So this is the forces there acting from 0 to 4 seconds. So we've got that. We also need to figure out what's happening with that moment being applied. So we'll go from 0 to 4 seconds, 8t dt. And that will equal our final angular momentum, which is mass times velocity. So 10 times v2 times distance, 0.5. And once again, we have two of those. So this will be our equation. Let's take the integrals here. Let's see, half of 2 is 1. So we end up with 10t. Oh, let me go back to black for that. Oh, let's see, I can do this. Half of 2 is 1. So we've got 10. Take the integral, becomes 10t. And this will go from 0 to 4. And we'll add to that the integral of 8t, which becomes 8t squared over 2, evaluated from 0 to 4, equals, let's see, half of 2, once again, is 1. So this will equal 10 v2. All right, so 10t evaluated at 4 minus 10 times 0, so I'm not going to write that. 8t squared over 2, now 8 over 2, as we know, is 4. So I'll have 4 times 4 squared minus 4 times 0 squared, so I won't even write that, equals 10 v2. So we've got 40 plus 64 equals 10 v2. 40 plus 64 is 104. Divide by 10, and we get that v2 equals 10.4, and those would be meters per second. So that would be the final velocity after 4 seconds due to the impulse for those 4 seconds of applying two 10 Newton forces and a moment that is 8 times the time. So that might be how we would work through a problem like this. Start with your initial function, write that out, just like we've been doing all semester, and put in any knowns and the unknowns, and then work your way through the problem. And that seems to work pretty well. Let's take a look at what they came up with, see if we did something similar. They wrote the equation much as we did, and they note that the initial angular momentum is 0. They also took an integral from 0 to 4 of 8t, and 2 times 10 times 0.5 equals 2 times 10 times 0.5 v2. I called it v2, they just call it v. And they worked it out the same as we. So that is how we will look at these conservation of angular momentum problems. We did have a sample problem in class, and it turned out much the same. While this is a 3D problem, it really is two balls on the end of a rod that are rotating around a central axis, just like we had before. So it actually works out the same way. These also are 10 kilogram balls. They give us, however, the initial velocity. Now, the first one started from rest. This one starts at 2 meters per second. So we will have an initial angular momentum to apply. They give us the final time is 3 seconds and so on. And so it works out just the same. They found angular momentum 1 and 2. 2 has the variable v in it. We've got our angular impulse applied from 0 to 3 seconds. Add those together and solve for v. And it works pretty well. So that's our final section from chapter 15. Take a look at that, look at the homework, see if you have any questions, and let me know if you do. Enjoy.